Decision trees are one of the most popular techniques for predictive classification. This video will not cover exactly what decision trees are or explain how they work. I assume that you already know that. But this video talks about some of the advantages and disadvantages of decision trees and looks at some alternative approaches that can also be used for predictive classification. So first, the advantages of decision trees. First, they are easy to use and understand. As I showed in other videos, going through them, looking at how they work and how you can apply it is very straightforward. So they're relatively easy to understand after relatively little effort in applying. Then also significantly, decision trees produce rules that are easy to interpret and implement. So they're an upside down tree that splits based on decisions and goes step by step, and especially shallow decision trees that are not too deep, like this one here is just 4-level deeps. It is quite easy to interpret and implement them. Now, this is actually very important from a managerial perspective because you might be someone who creates decision trees and using some basic tools, but you're probably bringing these results to your manager who probably does not understand decision trees or how they work. But if you can present a simple tree like this one here, and you can explain the business decisions behind them, then your manager can understand them and can validate the decisions that you are trying to convince them of based on your analysis. And that's very significant because that is not the case for all machine learning techniques. They are not always easy to interpret and understand how they came about the results. And without that, it's hard to have confidence on any decisions that might be inferred from them. Another advantage of decision trees is that variable selection and reduction is automatic. That is, you might have a data set of 20 variables, so 20 features, and you don't have to think about which ones are significant. You give them all to the decision tree. The decision tree figures out which ones are important and ignores the rest. In a lot of other machine learning techniques, if you give them too many variables, they're going to try to make sense of everything and end up in the mess. So you need to think in advance somehow which variables are important or not before you do the algorithm. Decision trees figure that out automatically for you. Decision trees also do not require the assumptions of statistical models such as normally distributed data and so on. And so they work with a lot of different data sets. Significantly, they can handle numeric and categorical data no problem. Most machine learning techniques require you to work only with numerical data. And if you have categories such as in this example here, you have categories such as education level, which is not just a strict count, then you have to convert them to numbers in order for them to work. But decision trees, you can give them categories such as north, east, south, west. They figure them out automatically. And related to this, decision trees is one of very few algorithms that can handle most missing data automatically. So that is, you don't have to fix your missing data before the decision tree works with it. And that's because the decision tree just treats missing data as data. It says that some values are missing and that might actually determine some outcomes. So it's very flexible in working with missing data. However, all is not rosy. There are also some disadvantages of decision trees that you need to realistically understand when you use them. First, they may not perform very well when there's some kind of structure in the data that does not work horizontally or vertically in splitting the data. And this is a little bit hard to explain, but it has to do with the way decision trees work. The fact that each variable is orthogonal to the others. And in practice, it just means that some data sets you give decision trees might not come up with good predictions because the nature of that data doesn't fit that very well. A related issue is that because the various features, so in this example, there's income, education, and family, because the decision tree treats them and looks at them one by one at a time, if there are interactions among these variables, that is, you have to consider them at the same time, decision trees don't work well with that. So for example, if customer purchases depend both on their age and their level of education, and this might be the case where perhaps people with higher income uh, and higher education have one outcome, but people with lower income and lower education have a different outcome from people only with higher education or people only with lower education. When you have to look at them both at the same time to find significant effects, decision trees do not capture that very well. Again, that comes out to the result that some data sets will not be able to be handled very well by decision trees, and they will not have good predictions. Now, that said, there are some advanced versions of decision trees to be aware of that can handle some of the limitations of the more simple versions. First to know about is the regression tree. Strictly speaking, a decision tree is called a classification and regression tree because it's not only for classification, that is for determining categories. With simple adaptations, a decision tree can handle numeric values and can make numeric predictions. So it works in a similar way, and this is a very good benefit because that means that the other advantages of decision trees can apply to regression to numeric estimates of problems. Another type of advanced decision tree that mainly improves the accuracy of decision trees is that instead of using just one decision tree, like you have in this diagram, you create lots of decision trees and you get a composite outcome from them. Two main approaches to doing this are first, here you have a random forest where the algorithms attacks the same data sets, but they just make small changes in the parameters or in the data so that each tree created from the data is slightly different. And you might grow a forest of 50 or 100 trees, and each tree estimates its answer on the data, and then the average or the mode or the most frequent answer becomes the one that the entire random forest gives. And generally that gives much more accurate results than a single decision tree. Another approach of combining trees is that with a gradient boosted tree, you create your first decision tree, and then you take notes. Well, this is done automatically by the algorithm. The algorithm takes note of the data which the decision tree did not predict so accurately, and then it creates a second tree that focuses on the weaknesses of the first one, tries to improve on them, and then it creates a third tree that focuses on the weakness of the second one and tries to improve on it, and keeps on doing this for maybe 50 consecutive trees, and the final tree is much better than the first. And that's called a gradient boosted trees. And this is especially useful when the target variable is something that does not occur that frequently. So the last thing I'd like to cover in this video is looking at other predictive classification techniques beyond decision trees. So there is a rule induction whose outcomes can look like those of decision trees in the sense that it turns the results end up in a set of English language rules. And one way of doing rule induction actually is using the decision tree and reading the decision tree as a set of if and else rules. Another approach is logistic regression, which is a variation of linear regression that instead of trying to set a straight line to connect numeric values tries to predict binary categories, true or false, yes or no, using an algorithm similar to linear regression. Uh, K nearest neighbors, or KNN classification, is another approach that has a fairly good prediction generally. But one disadvantage is that in production, it's rather slow in producing predictions. And so it can be used for analysis of past data, but if you want instant predictions, it's not very good because of its slow speed. Naive Bayesian is another popular classification approach that has fast and generally accurate predictions and is very flexible in its input sources, but it does have a statistical assumption of the independence of inputs, which often is not the case in the real world, and that results in the fact that sometimes it does not have such accurate predictions because of the specific nature of the data set. Neural networks are another popular approach, including deep learning that simulates the operation of neurons in the brain to make predictions. And it has generally good predictions, especially when working with very large data sets. However, one of the main challenges with neural networks is that it can be very difficult to explain why and how it came out with the result. So it loses the benefit of interpretability and managerial plausibility. Support vector machines are another popular classification approach, which is quite good for graphical applications. And one advantage is that it's fairly robust against outliers. That doesn't affect its decisions very well. Though I will note that decision trees are also quite robust against outliers. So this is a perspective, and if any of these interest you, you could learn more about them. But decision trees are one helpful technique among many other classification approaches.